Welcome to solverfy.
Okay, so we know the ground state of the beryllium atom can be equal to Z over N to the power 2 times negative 13.6 electron volts. So Z here is the atomic number. We know the atomic number for the beryllium is 4, and N here is the quantum number, which is 1 at ground state. Okay, and negative 13.6 electron volt here is the ground state energy of the hydrogen atom. Okay, so now if we plug in back to the equation with the 4 and 1, we'll have 4 over 1 to the power 2, and then times negative 13.6 electron volts. And this will give us the ground state energy for the beryllium atom is about 217.6 electron volts. If we convert it to the first digit, which is the digit of for the integer, is 218 electron volts. Okay, and as you can tell, the ground state energy of the beryllium atom is 16 times the ground state energy of the hydrogen atom. And for question B, we know the ionization energy is equal to 0 minus the ground state energy. And so in this case, it's just simply equal to 0 minus negative 218 electron volts. Okay, which is 218 electron volts. And by the way, here I should put a negative sign here. Okay, because the calculation was negative. So therefore, the ionization energy for the beryllium atom is 16 times the ionization energy of the hydrogen atom. Okay, and the ionization energy for the beryllium atom is 218 electron volts. And for question C, well, we know the wavelength of the hydrogen atom, which is lambda h here, can be expressed as lambda h is equal to hc over E2 minus E1. Okay, since hc over lambda h is equal to E2 minus E1. So we know h here is the Planck constant, c is the speed of light, E2 is the energy at a level 2, and E1 is the energy at level 1. So therefore, we'll have hc over lambda be, which is the wavelength of beryllium, is equal to z squared times E2 minus E1. And as you can tell, this term here is actually equal to this term. So therefore, we can use hc over lambda h, substitute for E2 minus E1. So we have hc over lambda be is equal to z squared times hc over lambda h. As you can tell, hc can be cancelled out. And this will give us 1 over lambda be is equal to z squared over lambda h. So lambda be is equal to lambda h over z squared. So we know the wavelength of the hydrogen atom is given as 122 nanometer, and the z, which is the atomic number for the beryllium, is 4. So therefore, if we plug in back to the equation, we'll have the wavelength for the beryllium atom is equal to 122 nanometer over 4 to the power 2, which will give us 7.625 nanometer. If we round it to the second digit up to the decimal point, we'll have 7.63 nanometer as the wavelength for the beryllium atom during the transition between n equal to 1 and n equal to 2. And for the last question, well, we know the radius of the beryllium atom can be equal to 1 over z times the radius of the hydrogen atoms, which is 1 over 4 times the radius of the hydrogen atom, since we know the atomic number of the beryllium is equal to 4. And these are the answers for this question.